Hi, I am Vijay Chaudhary. I am an applications engineer in the Power Products division of Texas Instruments. Today in this video I am going to talk about the flybuck DC to DC converter topology and show you how and when to use it. The flybuck topology is very useful in creating multiple bias rails, one or more of which can be isolated. I will start by explaining what a flybuck topology is, its operating principle, and its advantages compared to other competing topologies. The flybuck topology is essentially a synchronous buck converter where the primary inductor has been replaced with a coupled inductor. The primary output voltage is dependent on the feedback resistor divider, just like in a buck converter, and the secondary output is created by rectifying the secondary winding waveform with the help of a diode D1 and the capacitor Cout2. The secondary output Vout2 is related to the primary output voltage by the transformer turns ratio, and there is a term for diode drop D1. In the next few slides we will explain the operating principle of a flybuck topology. In this picture on the left hand side we have the output power stage of a flybuck converter, which shows the switch nodes 1 and 2, the coupled inductor, and the output capacitor Cout1 and Cout2. On the right side are the operating waveforms of a flybuck converter. On the left side vertical axis we have the quantities for the primary side of the converter, switch node 1 and inductor current L1. On the right hand side axis we have the secondary side quantities, switch node 2, Vout2, isolated ground, and the current in the secondary winding. Also shown is the magnetizing current in gray. The operation of a flybuck converter can be divided in two subintervals in every switching cycle. When the high side switch is on, the subinterval is T on, and when the low side switch is on, its subinterval is called T off, or the off time. The on time is highlighted in this slide. During on time, the switch node 1 is connected to the input voltage Vin. During this time, the inductor current charges the output capacitor of the primary output, and because of the polarities of the diode, the secondary diode is reverse biased. During on time, the operation of the primary side is identical to a buck converter and the secondary current is 0. In this slide, the T off subinterval is highlighted. During T off subinterval, switch node 1 is connected to ground and the primary output voltage appears across the primary winding. Because of the polarities of the inductor winding, the diode D1 becomes forward biased, and the primary capacitor Cout1 charges the secondary capacitor Cout2 through the leakage impedance of the coupled inductor. The regulation of the secondary side happens in the second subinterval when the primary output capacitor is effectively connected to the secondary output capacitor. The black waveform shows the current in the secondary winding. The gray waveform is the magnetizing current of the inductor, and the primary winding current is the sum of the magnetizing current and the secondary reflected current, which is shown in blue here. One of the main advantages of a flybuck topology is that it does not require any optocoupler or tertiary winding feedback to regulate the secondary output. This results in significantly smaller solution size for a flybuck converter. In this slide, we compare a 3-watt isolated bias solution, one utilizing an LM5017 based flybuck converter and the second one utilizing a flyback topology. The flybuck converter, because it's based on constant on-time control scheme, does not require a compensation design. The flyback converter, on the other hand, requires a complex compensation design. The flybuck topology is a buck-derived topology, and therefore it is more tolerant of the leakage and less susceptible to the noise. The flyback topology, on the other hand, is very sensitive to leakage inductance of the winding and usually requires a snubber to suppress the spikes caused by the leakage inductance. The flybuck topology requires a 2-winding transformer for 2 outputs, whereas a flyback topology requires a 3-winding transformer for 2 outputs. In addition, the flybuck topology transformer turns ratios are even, whereas the turns ratios in the flyback topologies are very asymmetric, which results in a much smaller magnetics design for flybuck compared to the flyback topology. All these add up to give the flybuck topology significant advantage in terms of the part count and solution size. As we can see here, for the similarly power design, the flybuck converter requires only 15 parts compared to 23 parts for a flyback solution, and the required board area is also much smaller. For more information on how to design a flybuck converter and supporting material, please visit the links on the next page. Thank you for your time.